Standard conditions. So gases have a lot of, well, they've got these 4 variables that we have to specify. And so as a convenience, we've established something called standard temperature and pressure. And it's abbreviated STP for standard temperature and pressure. Standard pressure is 1 atmosphere. That's 760 torr. Standard temperature is 273, should be 0.15 Kelvin, or 0 degrees Celsius. The way I remember this is the temperature and pressure something would be if it was open to the atmosphere in an ice bath. Okay? A lot of this stuff was done before technology. They didn't have heating and cooling chambers and stuff, and how do you hold something at a constant temperature? You put it in a big vat of ice water, and it'll be 0. Easy peasy. And what's the easiest pressure to have? Atmospheric pressure, 1 atmosphere. STP is useful for making comparisons between gases. So we've talked about molar mass, right? That's the mass of 1 mole. The molar volume is the volume of 1 mole of a gas at standard temperature and pressure. What would the volume of 1 mole of gas at STP be? How could we calculate that? Could we use the ideal gas law? Sure we could. PV equals nRT. We want to find the volume of 1 mole. Okay? So the volume of 1 mole, volume is equal to nRT over P. Well, how many moles? 1 mole. And we're going to say exactly 1 mole. Ideal gas constant, still the ideal gas constant, 0.8206. How many sig figs does that have? 4. That's not an exact number. What's the temperature at STP? 273. I'm going to do 273.15 Kelvin. And the pressure at STP? Exactly 1 atmosphere. So the volume equals 22.41 liters. Any gas, 1 mole of any gas at 0 degrees Celsius and 1 atmosphere is going to occupy 22.4 liters. It's kind of hard to visualize 22.4. It would be a cube about this big. So like a big moving box that you pack pillows or something in. 22.4 liters. Why does it work that way? We'll get to that, but let's just answer it right now. It's because the size of the particles don't matter. Because there's so much space. If you've got helium, which is really small, or if you've got xenon, which is a really big atom, it doesn't matter because of all the empty space in between. So the molar volume of any gas at STP, we usually round it to 3 sig figs, I'm not sure why, is 22.4 liters per mole. This is a super useful conversion factor. It can save you from having to drag out the ideal gas law over and over and over again. And we know that 1 mole is 6.022 times 10 to the 23rd molecules or atoms of a gas. The identity of the gas doesn't matter. What will be different is the mass of the gas. Okay? Here we have pictures. So here's helium, xenon, and methane at STP. 22.4 liters for 1 mole of each of them. They don't all weigh the same though. How much does this 1 mole of xenon weigh? 131.3 grams. How much does this balloon full of helium weigh? 4.003. And this one would be 16.01 grams. Same number of gas particles, same pressure, same temperature, same volume. The masses will be different because the mass of the individual particles is different. Which brings us to density. I mentioned earlier that when you heat up a gas, its density decreases, and that's why hot air balloons rise. Density, remember, is mass to volume. For gases, we usually give that in the units of grams per liter to make the numbers nicer. Solids and liquids use grams per milliliter. The mass of 1 mole of a gas is equal to its molar mass, right? So 1 mole of gas. And the volume of 1 mole at STP is 22.4 liters. So at STP, we can calculate the density easily by taking the molar mass and dividing by the molar volume of a gas. So if we looked at helium and nitrogen, the helium would have a density, we take 4 grams per mole divided by 22.4 liters per mole, we'll get a density of 0.179 grams per liter. Nitrogen, each nitrogen molecule weighs a lot more, 7 times more, and so its density is greater. This is an absolutely fine way to calculate density. That's not how I think about it, though. That's kind of a shortcut way. I think, okay, the density is the mass divided by the volume. And I'm going to say, okay, well, I'm just going to pick an amount of gas. I'm going to say, let's say I have 1 mole, because I think that would be easy. Let's do neon. What's the mass of 1 mole of neon? 20.18 grams. I'm just choosing 1 mole. And then this is at STP. What's the volume of 1 mole of neon? 22.4 liters. And so I can calculate the density that way without having to remember a special equation. And so that one comes out to be 0.901 grams per liter. Any questions? The density of a gas is proportional to its molar mass, because the heavier the particles are, the more dense it is. And so you can derive that like this and end up with this. The density equals the pressure times the molar mass divided by RT. If you want to remember that equation and use it, you go right ahead. I'm not going to use it in class. Calculate the density of xenon gas at a pressure of 742 millimeters of mercury and a temperature of 45 degrees Celsius. Calculate the density. What's density? Density equals mass divided by volume. Okay. I've got xenon gas, I've got a pressure, I've got a temperature. Let's write those things down. Pressure equals 742 millimeters of mercury. Temperature is 45 degrees Celsius. Those are important because if you change the pressure, you change the temperature, you're going to change the density of the gas. I need mass, I need volume. All I need to do is choose a quantity, choose 1 mole, because it's easy. So choose 1 mole of gas. What's the mass of 1 mole of xenon? The molar mass, right? Periodic table was 131. 0.3. Well, that was easy. What's the volume of 1 mole of this gas? It's not 22.4 this time, is it? This is not STP. The volume of a gas is equal to nRT over P. If you use the ideal gas law. Well, N is 1, exactly 1 because we picked that. R, 0.08206 liter atmospheres per mole Kelvin. And there's our suggestion for units. Is my temperature in Celsius going to be okay? Nope. Plus 273.15, 273.15, plus 45, 318.15 Kelvin. Divided by the pressure. I have to convert millimeters of mercury to atmospheres. And this is a conversion you need to memorize. We use it a lot. 742 divided by 760. 0.97632 atmospheres. I'm keeping track of the sig figs as I go along so I don't have to backtrack later. 0.97632 atmospheres. Check those units. Atmospheres are canceling, kelvins are canceling, moles are canceling. I end up with a unit of volume. So I've got 0.08206 times 318.15 divided by 0.97632. 26.741 liters. That's the volume of 1 mole of gas at this pressure and temperature. So then I plug that into my density equation. 26.741 liters. So I've got 131.3 divided by 26.741 equals 4.9101, which equals 4.91 grams per liter. That's the density. You can use that equation on the previous slide, but then you have to remember the equation on the previous slide. For me, it's easier to just think about it. I remember the density equation and the ideal gas law, and I'm just going to find the pieces I need and stick them into the density equation. How exactly you do it is up to you, but you should be able to show your work. Any questions?